So good morning, everyone.
Good morning.
Good morning.
Good morning.
So I hope you can see my document.
Yes.
So we stopped at page later, so I'm starting earlier. And we are talking about what would happen if we terminated a line with an arbitrary load where an arbitrary load is one which is supposed to be a complex load, so to speak, as the most general load that we can get. And we say that in this case, the minimum, the voltage minimum or the current maximum cannot occur at the termination, neither can the voltage maximum or current minimum occur at that termination. But we say that the standing wave pattern of the voltage and current waves can be extended beyond the termination until we get the termination or the voltage minimum or maximum. And the length of a line that of the fictitious line that we have, we can always attach that to a resistance, which we'll call Rm, or we can use a R big M, that is R greater than Z naught of that line, or R smaller than Z naught of that line when we are using a minimum. And therefore we can, as we have seen, that when you terminate a transmission line with a load or with a resistance, we can look at the input impedance at the input of the line, and we'll see that the line will have transformed that whatever the resistance, the termination, into a new input impedance, which you can always say that it will represent the ZL that we have for a particular case. So we say that this does not change the voltage distribution to the left of the actual termination, where Z is less than 0. And so, using Rm in place of Zl and Lm in place of L, we can therefore write the input impedance looking at our new additional length of line Lm. We can get Ri plus Jxi, which is equal to Zi. For that particular case, that's equal to Z naught Rm over Z naught plus J, okay? That is Rm plus J Z naught, tangent of beta Lm over Z naught plus J Rm tangent of beta Lm. Of course, remember that whenever you are using the actual trigonometric functions, we are assuming that our line is lossless. So the real and imaginary parts will then yield the values for Rm and the value of the length Lm that we have used to transform. Experimentally, we could also obtain this RM or the ZL, okay, by measuring the standing wave ratio and the distance minus Zm of the closest extremum, the voltage wave to the load. That is, an extremum we are saying either a voltage minimum or a voltage maximum, or a current minimum or a current maximum, but it's usually easier to measure voltage because we are using high impedance probes, so to speak. And therefore, all we are saying is that we get that the value of Zm, that is the position of the nearest voltage minimum or to the load, plus the length Lm must be equal to lambda by 2, as we can see here. Okay, that is, if we were to take this value here and we measure, then this position here will give us a value of Z lambda by 2, where because we say that for the voltage minimum to occur at this point, it must have traveled to the termination and back again. So when it does that, then it has only a, half a wavelength, so to speak. Thus, it can determine gamma from VSWR as lambda equal to, or gamma equal to S minus 1 over S plus 1. That is the magnitude of the reflection coefficient is going to be given by the standing wave ratio less unity over standing wave ratio plus 1. Then we'll determine the angle of the reflection coefficient from the position Zm that is closest to the minimum, to the voltage minimum. And we write it as theta gamma equal to 2 beta Zm minus pi. Because when you look at the equation for the Zin, you'll see that it will be multiplied by the root of the modulus of gamma multiplied by the minus of j 2 beta z plus j theta gamma, where theta gamma is of course the angle of the reflection coefficient. And this is for the case when we are looking at the first minimum. So then we'll determine the value of ZL as ZL equal to RL plus JXL equal to Z0 into 1 plus the magnitude of the reflection coefficient multiplied by the exponent of the angle over 1 minus that value there. And the distance of a voltage maximum to the termination, Zm, could also be used. And in this case, we have to do away with the angle pi, because now we are saying that the value that theta, or theta minus 2 beta Zm must be equal to 0, so that we can just get the magnitude alone remaining. And therefore, for the n equal to 1 to 0. So an example now. The standing wave ratio of a lossless 50 ohm line terminated in a non-load impedance is found to be 3.0. The distance between successive voltage minima is 20 centimeters, and the first minimum occurs at 5 centimeters from the load. Determine A, the reflection coefficient gamma, B, the load impedance Zn, and C, the equivalent length and terminating resistance of a line such that the input impedance is exactly going to be equal to Zn. In other words, all we are looking for is Lm and Rm that we are dealing with, such that when we terminate that Lm length of line with Rm that we choose, is going to give us a value of Zn. So the first part A is that the distance between successive voltage minima is of course going to be given by lambda by 2 for the reasons that I have given. And thus, lambda is just going to be given by 2 times the distance between successive voltage minima or voltage maxima, and we get a 0.4 meters. That is the wavelength, the operating wavelength of that line is 0.4 meters. Beta is going to be given by twice pi divided by the wavelength, and we see that that is going to be given by 5 pi radians. And the magnitude of gamma of the reflection coefficient is going to be given by that equation, that is this. The voltage standing wave ratio less unity over 1 plus the standing wave ratio, and we get a value of 0.5. And theta gamma, that is the angle of the reflection coefficient, is going to be given by twice beta multiplied by Zm prime, where Zm prime is being used to where we are measuring positively towards the generator, so to speak. And we get a value of 0.5 pi radians. And therefore, gamma is just going to be given by minus j 0.5. That is, it has an angle of 90 degrees. And B, Zn is therefore going to be given by that equation, which gives us a value of 30 and j 40 ohms. And C, we can always write that is going to be given by that, and we can express that as using the transformation, the impedance transformation expression to get the values of Rm and beta m. And then we equate the real parts and imaginary parts of that. But if we recall that Zm prime plus Lm is equal to lambda by 2, and Rm is going to be given by Z0 over the standing wave ratio if we used Rm less than Z0, but if we used Rm greater than Z0, we have, and then using the voltage maximum, we multiply that one by the standing wave ratio. And hence, we can always get that Lm is going to be given by lambda over 2 minus Zm prime. And this, since we have been given the voltage minimum, the position of the voltage minimum from the nearest the load, we can now just subtract straight away and get that value. We don't have to express this, to use this equation, okay? But if for those of us who like calculations, can always revert to this kind of value, okay? And hence, and Rm is going to be given by the characteristic impedance of the line divided by the standing wave ratio, and we get a value of 16.7 ohms. What I expect you to do as an exercise is try and use this equation and see whether you get the same value that I have here using the measurements. But see, remember that Lm prime equal to Lm minus lambda by 4 would also give us a value for the standing wave ratio if we were to use the voltage maximum, and then we can get a value for that value as 150 ohms. So these two are also valid solutions when we use the maxima positions instead. Now, transmission line circuits. Now, when we are looking at transmission line circuits, we want to see what would happen when we deal with voltages or signals for which the wavelength is of the same order of magnitude as the size of the circuit itself. In other words, we are talking about circuits that are of large electrical lengths, so to speak. So we seek to express the voltages on a line that is terminated in a load Zn in terms of, one, the source parameters, which are the generator open circuit voltage Vg and the source, the generator source impedance Zg. Two, the line characteristics, which are given by the propagation constant on the line, the characteristic impedance, and the length of the line. And finally, the load impedance. In many cases, we'll know what the load is, and we'll work backwards. So, if we look at Z equal to minus L, that is at the source, or the sending end of the line, then we can write that the input impedance Vi is going to be given by the open circuit voltage of the generator less the voltage drop across the source impedance Zg. That is Vg minus Ii and multiplied by Zg. And this must be equal to the line current at that voltage or at that position, which we saw already was going to be given by IL by 2 Zn plus Z0 multiplied by the exponent of gamma n into 1 plus gamma, exponent of minus twice gamma n. Remember, Now this equation here comes from the value of V plus, okay, or that is the value of Vz divided by the current, so to speak. And the current II is going to be given by the same kind of equation where we had 1 minus gamma exponent of minus Z to gamma L. Now, we can therefore express what this factor here, because this factor is common to both the voltage, the input voltage and the input current, we can express this in terms of the other values, okay? And therefore, we can see that this is going to just be given by Z naught Vg over Z naught plus Zg in multiplied by 1 over 1 minus gamma g and gamma multiplied by gamma and exponent of minus 2 gamma L, where gamma g now will be called a generator reflection coefficient, or the reflection coefficient at the sending end of the line. Okay, and it's given expressed as Zg minus Z naught divided by Zg plus Z naught. Okay, and it will be called the voltage reflection coefficient at the generator end of that line. Now, at any point Z from the load, we have that Vz is going to be given by Z naught Vg over Z naught plus Zg multiplied by 1 plus gamma exponent of 2 gamma z over 1 minus that. That is, we are multiplying that one by the equation for the current, okay, that we have already found in the other place. And you can see that this is going to be given by the exponent of mana gamma into Z plus L. Remember, it's because we are already choosing our Z at the generator, at the load end, and therefore we must add that value of L there. So, and the current, the line current, is going to be given by the same expression, but now note the only thing that is changing is the factor 1 minus gamma exponent of 2 gamma z. Here it's plus and here it's minus, and we are multiplying the same value. So, an example now with that kind of case. 100 megahertz sinusoidal generator with an open circuit voltage Vg given as 10 at angle 0 volts and source resistance of 50 ohm is connected to a lossless 50 ohm air line 3.6 meters long and terminated in a load that is 25 plus J25 ohm. Determine Vz at the location Z from the generator, and B, the Vi, the input voltage at the input terminals of the line, and BL at the load, as well as C, the voltage standing wave ratio on the line, and finally the average power that would be delivered to the load. What we can see, the information we have here is of course the value of the operating frequency and therefore the operating wavelength, and also we can get the propagation constant. We know what the voltage is, the open circuit voltage of the generator, and we know that the line has an input and it has a source impedance of 50, and our load, our line is also 50 ohm. And therefore it means that gamma g that we have calculated is going to be 0. In other words, we can say that the generator is matched to the line, okay? And it's an air line, therefore it has an air dielectric, not so the epsilon r is going to be unity, and the length is of course given there as 3.6. Okay, so we have that Vg is equal to 10 volts at angle 0. Zg is 50 ohms. The frequency is 10 to the 8 hertz, and Z0 is 50 ohms. Zl is 25 plus J 25 ohms, and we can always convert this one into the polar form, okay, magnitude and angle, and we get 35.36 at an angle 45 degrees. And the length of the line is 3.6 meters. And therefore beta can be computed as twice pi by lambda, which is just the same as saying omega over c, and we get a value of 2 pi by 3, that is 2/3 pi radians per meter. And therefore, if we multiply that one by the length of line that we have, we get a value of 2.4 pi radians. So beta L is what we refer to as the electrical length of that line. Gamma is going to be given by the load impedance less the characteristic impedance over the load impedance plus the characteristic impedance, and we get a value of 0.447 at an angle of 116.6 degrees. And gamma G is of course going to be equal to 0 because it's Zg minus Z0 over Zg plus Z0, and Zg is equal to Z0, so that is going to be equal to 0. Since the distance from the load is Z equal to minus Z prime, and the source is at Z equal to minus L, then the point of interest is at Z prime from the generator with Z prime equal to 0 at the generator and L at the load. That is, Z prime and Z are measured in opposite sense. That is, we are measuring Z prime from to be 0 at the generator and going towards the load, and Z is measured at the load and becomes negative as we go towards the generator. And therefore, when we place those values of Z prime into the equations for the line voltage, we get that kind of expression there. And B, VI is therefore going to be given by V0, and this is just going to be given by Z0 VG over Z0 plus ZG, and multiplying that by an equation there. And what we get is that we get a value of 7.06 at an angle of 8.38 degrees, and that is volts. Okay. And the load voltage, VL, is going to be given by V at Z prime equal to L, and we get a value of 4.47 at an angle of minus 45.5 degrees. And C, the standing wave ratio is of course given by the expression there as we defined it. That is, we are taking the magnitude of the reflection coefficient, we get a value of 2.62. And finally, the power, the average power delivered to the load is of course a half the real part of the voltage, or the load voltage multiplied by the complex conjugate of the current, and we get a value of 0.2 watts. Now, if ZL was equal to 50 ohms as well, that is, that the line was also matched to the load, then the gamma would be 0, that is, the reflection coefficient would also be 0, and VL would therefore be equal to VI, and it would be equal to a half of VG, or the open circuit voltage of the generator. And therefore, in this particular case, when we have a maximum, a matched load to the line, then maximum power would then be delivered to the load, because the input power to the line would be absorbed by the load, okay, at the load as well. And therefore, P average maximum is equal to VL squared by 2RL equal to 0.25 watts. This is usually called the maximum available power, okay, from that generator. Whenever we have a generator and we matched it everywhere, we'll get a maximum power that will be available to the load that would be given by that value. The reflected power is therefore, because ZL is not equal to 50 ohms, the reflected power is just going to be given by the modulus square of the reflection coefficient multiplied by the maximum available power, and we get a value of 0.05 watts. So now we come to another concept that is usually very confusing to many students, and this is because many times from circuit theory you've always been dealing with equations of, say for example, if I have an RLC circuit, say a series RLC circuit, I would get that the impedance is going to be given by R plus J omega L plus 1 over J omega C, okay? If it was parallel, of course, it would have the usual expression as well. Now, many times you'll find that the students would get very confused, especially when we say that we have transient conditions on that line. Or rather, sometimes, say for example, if that circuit was to be driven by a switching signal such as a square wave, then the impedance concept loses meaning. It doesn't have any meaning at all. Okay? We can use Fourier transforms to try and convert the signal into a Fourier transform and then use the impedance concept. But when we have transients, then you see that Fourier transforms cannot work because Fourier transforms assume steady state operation. And therefore, you would have to go into Laplace transforms and so forth. So, when we have transients on the line, the concept of reactance, wavelength, wave number, phase constant, all lose meaning under the transient conditions or non-sinusoidal line operations. Important practical situations where these signals and sources are not time harmonic and the conditions are not steady state would include such cases as we excite the line with digital pulse signals, say for example in a computer network. The computer, of course, the digital signals are alternating or switching signals, usually trapezoidal. And this, therefore, it means that we cannot represent them by a single frequency. If we want to represent them in the frequency domain, then we must include the fundamental frequency as well as an infinite number of harmonics. Okay? And therefore, at each harmonic, there will be an impedance for that harmonic. Okay? And therefore, this reactances lose meaning for that case. Another case would happen when we have a power surge on a line or a telephone line. Say, for example, if a transmission line is struck by lightning, the voltage will go higher up first and then die down to the steady state value later. Okay? So in that condition, when we have that transient, we cannot use those kind of, we cannot call the line as sinusoidal or time harmonic or harmonic time dependent signal operation. So we are going to look at this in two ways. We'll consider lossless lines, and we'll start this with a simplest situation where the line is being operated. That is, we are connecting a DC generator to a resistive load, Z0, okay? And we switch it on at time t equal to 0 as shown there. So we have a DC load of voltage VDC, that is open circuit voltage VDC. We have a load resistance or a source resistance of ZG. Here I'm using ZG, but we can always write it as RG. We have the line section that we are connecting it to the load Z0 as having a length L, okay? And we are measuring our Z at Z equal to 0 at the load. It has a characteristic impedance of Z0. We are, of course, since it's lossless, we can always say that the phase propagation constant is going to be beta, okay? Beta and Z0. Now, we want to see the line voltage at a position from the load. That is, we measure Z1 up to that point, and we look at what the voltage or the line voltage and line current will be at that particular position. And therefore, what we have done, we have just switched it on first at t equal to 0. It's more like what we say about the Big Bang, when the short man above said, "Let there be light." What happened? Did the light just go into steady state immediately, or what happened? Okay, that's what we are trying to see at this particular time. What happens immediately? We switch the generator onto the line. So the impedance looking into the line from the source end is going to be equal to Z0 and a voltage wave of magnitude V plus, V1 plus equal to Z0 over Z0 plus ZRG VDC will propagate down the line in the positive Z direction at a phase velocity Vp given by 1 over root of L prime C prime, where these are, of course, the per unit length inductance and capacitance of the line. and a corresponding current wave would be generated, okay, that will accompany that V1, the positive going voltage, and it will be given by V1 divided by Z0, and we see that that's just VDC over Z0 plus RG at Z equal to 1. Okay, so the plot of V Z of 1 as a function of time is then going to be a delayed step function at t equal to Z1 divided by Vp. That is, the voltage does not immediately rise to the input voltage or to V plus or to V1 plus immediately you switch on. It takes time for it to travel from the point of connection to the point that we are dealing with. And it's more like when you look at the eclipse of the sun, or is it called the eclipse of the sun, when we have the moon now covering the sun from Earth, and then the moon starts moving away from the covering, and we see that the shadow will keep on moving forward. That is, the lighted areas move as the moon is moving away. So even this particular case, our signal will be moving, raising up the voltage on the line from 0 to the value, to the actual value of the line voltage. Okay, and the current would also have a similar shape. So when the voltage and the current waves arrive at the load end, okay, they suddenly find that actually the load, the line is terminated in the characteristic impedance of the line, and therefore they suffer no reflection, and therefore the transient will die there. So a steady state will then be established with the entire line tied to a voltage V1 plus. Okay. Now, the problem happens when we have that the load impedance and the source impedance of the generator, that is here I'm using RG and RL, are different from the line characteristic impedance. Then we see that, one, if RG is smaller than Z0, or if RG is different from Z0, we'll first of all have a generator or a reflection coefficient at the sending end. Okay? When the wave arrived at the load as well, it will also find that the load is different, and it will suffer a reflection, and it will start moving backwards towards the generator. That is, we'll have a reflected wave component that will be traveling backwards towards the sending end of the line, where it finds again that there is a reflection because the RG and Z0 are different, and it will be reflected back again and so forth. And it keeps on going back and forth, just like, two guys playing ping pong, so to speak. So, when the switch is closed at t equal to 0, the source end will then send a voltage wave with a magnitude given by V1 plus into Z0 over Z0 plus the RG VDC. The reason why we are using Z0, the characteristic impedance of the line, is because the voltage has no knowledge of what is at the end of that line. And therefore it sees the line as an infinite line with a characteristic impedance of Z0, and therefore all it sees as terminating the generator is a load impedance of Z0. So this will propagate at a phase velocity v given by the same value as we saw before, okay? And it will proceed as if this line was infinitely long or matched. When it arrives at t equal to big T, which is equal to the length, the line length divided by the phase propagation, the phase velocity, okay, the wave will arrive at the load and find that actually the load is different from the characteristic impedance of that line, and therefore there will be a reflected wave component that will be generated at that position, and it will have a magnitude of V1 minus equal to the reflection coefficient gamma L multiplied by V1 plus, and where gamma L is equal to RL minus Z naught over RL plus Z naught. Okay, so we now have a reflected wave now traveling backwards. Now, depending on the sign of gamma L, it may reduce the line voltage as it's going back, or it may add to the line voltage as it moves back if gamma L is positive, so to speak. So the reflected wave arrives at the source end at t equal to 2t, okay, where it suffers reflection again, and a new wave propagating in the positive z direction will be again established with a magnitude given by v2z equal to gamma g multiplied by v1 minus, and this is going to be given by gamma g multiplied by gamma l and multiplied by the initial incident wave at the line, with gamma g given by that by definition. And this will go on indefinitely with a reflection at both ends at the line at t equal to nt, where n is equal to 1, 2, and to infinity. Some of the reflected waves may have negative amplitudes because gamma g or gamma L could be negative or positive. So unless the termination is a short or an open circuit, gamma g and gamma L will always have less than unity. They are always having a value less than unity, and therefore the reflections will grow weaker with time. At any location Z1 on the line from the source, the voltage and the current on the line, or the line voltage and the line current at a given time interval are then going to be given by all the components that would be appearing at that plane, which would be V1 plus V1 minus V2 plus V2 minus, and so forth. And the current would be given by the same. And the ultimate voltage across the load as the time progresses will then be given by, we are now using Z1 at the load, and you'll see that this is going to be given by that equation there, which we can always separate into even multiples, that is gamma g gamma L plus gamma g gamma L squared, and the other case where we have a gamma L coming out. That is, we'll take that one and the next one and so forth, and then we'll take that and factor it out, and you'll see that the two of them look alike. And what we'll see is that when we sum this one, you can use this, the sum of this kind of values where we have these are less than unity, gamma L and gamma G are less than unity. We can see that this will converge to a value given by 1 minus gamma G gamma L. Okay, so in the end, we have VL is going to be given V1 plus 1 plus gamma L over 1 minus gamma G multiplied by gamma L. Okay, so I can give you another exercise to go and try and get the sum of this equation here, where this is added from up to infinity. That is, when you take these functions here, that is the exponent goes up to infinity. Then you add them, okay, add them up and get the sum. You'll see that it will become something that like 1 over 1 minus gamma G gamma L. So an example is as follows. RL is 3Z0, RG is 2Z0, and gamma G is therefore going to be given by 1 over 3, and gamma L is going to be 1 over 2. And V1 plus is just going to be VD plus VDC divided by 3. And therefore, as the time goes towards infinity, that is, as we go to steady state, or what you used to call the final value, the final value of the voltage is going to be given by 9V1 plus over 5, which is just 3 VDC divided by 5. Similarly, if we were to use the current equation itself, we'll get a similar value as 1 minus gamma L over 1 minus gamma G gamma L, V1 plus over Z0, and this can be given as that equation there, which is just 1 over 5 VDC of Z0. Now, to try and follow how the reflection coefficients are going, or the reflections on the line are going, it becomes very difficult, especially when we are dealing with practical issues. Okay, so usually we use what we call the bounce diagram or the reflection diagram, where we have the voltage. Okay, we know that for a lossless line, the phase velocity on the line is constant, and therefore we can always write that at time t equal to 0, when we switch it on, we'll have a an incident wave that will go towards the load and arrive at the load at a time t, which is given by L over V, where the slope of that line is just V. And then it will be bounced back and with a reflection coefficient gamma L, and it will travel backwards at the same velocity V and arrive at the source end at a time 2t. Okay? And then it will be reflected again with a reflection coefficient gamma G and be reflected back, travel back towards the load and arrive there at 3t and so forth. So we can always use a graph paper, just draw our lines through, okay, with a slope of V. We don't have to even draw it to scale. All we have to do to make sure is that what we are using is the same, okay, it's constant all through, and then we can make certain assumptions to it. Now, if you look at this point here, Z1, this is the plane Z1 at the line of length L. So at this point, if we want to see, say we are talking about a time T3, the voltages that are appearing here, the line voltage that would appear on this plane, will be just those values of the voltages that the voltage components that we have there. So one will have the incident one here coming in, and then we have this reflected one coming in and so forth. So we'll just add all these ones together and get the value of the line voltage at time T3. If we want to get the time for a given voltage, again, we just draw those things coming out like that. So the only thing that is important to note is that bounce diagrams or the reflection diagram is not plotted in the usual sense. We usually put the time axis in the vertical line and the spatial axis as the horizontal line. This is more like what we deal with in the theory of relativity when we are talking about space-time diagrams. Okay. So the reflection diagram can be used to determine the voltage distribution at a given time, as well as the variation with time at an arbitrary point on the line. So to obtain the voltage distribution at, say, at time t equal to 4, we note that that value of t, that time is between the condition of the times 3t less than t4 and less than 4t. Okay? And therefore, we thus mark t4 on the time scale and extend it in a horizontal line to intersect the directed line of the voltage wave. Okay? Okay, below t equal to 4t, where t we said is L by V at P4, which has the value of gamma G, gamma L squared by V1 plus. So this is the component of the reflected wave at that particular time. So the vertical line will then be drawn from P4 to the z-axis to intersect at the point equal to Z1. And we note that in the range 0 less than Z1, from the source, the voltage has a value of V1 plus V1 minus plus V2 plus, okay? So we can see it here. That is at P4, we have only this voltage, okay? Then we have that voltage there, and we have that voltage there. And this one cannot be part of this. This one is beyond the time we are dealing with, okay? So the only one we have left is just this one, okay? This part here. Remember, don't say that because we are just about here, therefore we can include this one as well. We don't include this one at the top, we just include up to that point. Therefore, when we add these values together, what we'll get is that in the range beyond the Z1, we have only those voltages there. And therefore, the voltage discontinuity is hence just gamma G gamma L squared and V1 plus Z equal to Z1. That is, to one side, the voltage is higher than the other one. So the value of Vt is going to be like, would have a step. So hence, we can always write that the time evolution of that voltage is going to be given by this, the low value up to t, and then it increases to a higher value as we go towards the load again, because we have added a new reflected component onto the voltage there. Now, if the line is excited by a rectangular pulse of the form Vg of t equal to V naught into ut minus u into t minus t naught, where u is the step function, okay, the unit step function that you use, such a wave, of course, would be like, say, an interrupt signal. Say, for example, for your microcontroller, you have sent an interrupt signal towards your load that you are driving with the microcontroller, and therefore, how will it behave on that line, the line connecting the load to the microcontroller. So the transient response of the line will then be just a superposition of two. We are dealing with two waves. That is a step function that is positive, and then we are going to drive it down with a negative step function at a time t naught, okay, at a later time t naught from the first excitation, okay? So, an example then. A rectangular pulse of an amplitude 15 volts and duration 1 microsecond is applied through a series resistance of 25 ohm to the inputs of a 50 ohm lossless coaxial line. If the line is 400 meters long and is terminated in a short circuit at the far end, determine the voltage response midway down the line as a function of time up to 8 microseconds, and the dielectric constant of the line is 2.525. So L equal to gamma L is equal to -1 because we have short-circuited the line. Gamma G is going to be given by -1/3 because of the relationship between Rg and Z naught. And therefore, we have V of G is going to be given by 15 volts into U of T minus U of T minus 10 to the -6, where 10 to the -6 is the length L divided by the phase velocity on that line, where the phase velocity is just given by C divided by the square root of the electric constant. We get a value of 2.0 times 10 raised to 8 meters per second. And therefore, T, you can see, is going to be given by the length of the line divided by the velocity, and we get a value of 2 microseconds. And therefore, V1 plus equal to 15 Z0 over Z0 plus Rg. Yeah, this one is the width of the pulse itself, not the whatever the time of flight. So when we draw the reflection diagram, we see that the complete line is the positive going wave, okay? That is the positive wave, okay, that we have sent down the line. That is the first part. And then we apply at 1 microsecond later, we'll apply another wave that is negative, and it will go in that direction as well. Remember, the negative part is just the reflection diagram does not talk about the sign of the magnitude of the signals on the line at all. We are just dealing with how they are propagating on that line, okay? So, and that's why we have already labeled them with the value of the reflection coefficients, okay? That is the reflection coefficient for the positive wave, and that is the reflection coefficient for the negative wave. and so forth. So any disturbance on a line, I don't know what time I have, still have time. But so far, do we have any question?
Yes, regarding the rect function, the negative one.
Yeah.
Isn't it possible to just cut off the wave that is being transmitted? Like, doesn't it just go to zero at that 1 microsecond?
Now the question is, we are talking about transients. So you have switched on. Let's say you have switched on the line. So you have raised the voltage, isn't it?
Yes.
So when you switch off the generator, it will take time for that voltage to go to zero as well, isn't it?
Yes.
So that's why we can't just switch it off.
But the bounce diagram looks, doesn't that imply that we're still sending both?
Yes, both of them are being sent, but they won't matter. Look here, this is what happens. Let's see what I'm talking about. What I'm saying is this: we are driving our signal, our voltage, whatever, our line with a voltage that is going. Say for example, I don't know how to write it. You know how the step function goes?
Yes.
The step function is zero all the time at t less than zero and goes to unity at t equal to zero and continues.
Yes.
Now I can express this if I have a pulse of say delta t. Okay, I can represent it with two voltage sources, okay, which I'm superposing on that line. Okay, isn't it?
Yeah.
So the only thing for it to come to zero, all I need to do is to now, while I switch on my generator at t equal to zero to raise the voltage to the positive, and then at a time delta t, I apply another voltage that is negative to it, but of the same magnitude, going, okay, same magnitude by negative, and also going for all time. I'll leave it that way.
Okay.
So this is an equivalent representation of that rectangular pulse.
Okay.
Okay?
Yeah, okay.
So it really doesn't matter because after delta t, they all cancel to zero.
Okay.
Yeah. Any other question? So I see I have only 8 minutes left. So what I'll do is that I won't continue from there. I'll just stop at where we have reached today. We'll continue from there next on tomorrow. Is that okay with everyone?
Yeah, that's okay. Thank you.
Okay, so we'll look at that that expression there, or that example 11 tomorrow then. Okay, do have a nice day then. I need to go to another meeting. That's why I'm in a hurry. So I switch off, stop recording.